physics. Example, we're still in the static equilibrium topic. This example relates to tension, and so it's actually a really easy question. Looks hard, and it's certainly a odd situation. Here's our application. You've got two blocks. One is sitting here on a desktop. There's this point from which the second block B is hanging, and then they're both also connected to the wall through this diagonal rope at some angle. And so we don't know that angle. The things that we do know is we know the force of gravity on the block resting. Okay, block A has a weight, so that's just the force of gravity. And block B has a weight of 2.8 newtons, so that I have here, FGB is 2.8 newtons. And we know that the force of static friction holding the system in equilibrium is 1.4 newtons, right? So it would be acting in this direction, away from P. So before we go, well, let's look at the question and I'll tell you why we talk about tension. So it asks for a free body diagram on B. We're looking at tension in the vertical rope, tension in the horizontal rope, and tension in the angled rope. And we've never really solved for tension before. Tension is pretty easy. There's not anything fancy about it as far as calculations. What it is just a pulling force. And direction changes depending on sort of what object you're talking about. We generally give it the symbol Ft. You may see later I get lazy. I just call it capital T, which is sometimes annoying for students who don't like using T for period, T for temperature, and then I throw it in for tension. I think there might be something else that shows up for as well, but either way, it should be Ft, okay? And the thing with tension is, in this particular rope, say we did a free body diagram on this guy here, well, the same tension is in the string rope, no matter where you are holding and what direction you're pulling, at least from a magnitude point of view. However, on guy A, the tension is in the right direction, and if we did a free body diagram on guy B, the tension would be in the left direction. So tension is weird that way. The direction depends on what object you're talking about. But if you know the tension on guy A, then you also know the tension on guy B. It's just that it's the opposite direction. It's the same magnitude. Okay, the number's the same, it's just the direction that's different. And there's not much else to say about tension. We just do, it comes up in a few upcoming examples, and that's how we treat it. So to begin this problem though, we want to do first a free body diagram on block B. And so, sorry, I'm jumping around, but block B of course is the one that's hanging. And so there's not many forces acting on it, just gravity down, and we know its gravity is 2.8 newtons. And then there's the tension in the vertical rope is the upward force pulling up on B. Okay, so to solve for the tension in the vertical rope, that's what we're asked for in part B. Because the system is in static equilibrium, it's not moving, so you can say up equals down. Therefore, the tension in the vertical rope must be 2.8, must be equal and opposite. Okay. Part C asks us to do a free body diagram on block A. Now block A is a little bit different because it's resting on the table. I'm just going to jump up here, so hold on. Block A sitting right here, so it's got the tension of this rope. I thought you couldn't assume that these two tensions are the same. Okay, generally in a system tension is constant, but because of point P, and this connecting rope, you can't say these two aren't the same. But you do have a tension pulling on A, and you've got static friction sort of maintaining the equilibrium. And we got gravity, and because A is resting on the surface, we also have a normal force. Notice B wouldn't have a normal force because it's not resting on a surface. So that's all I'm drawing here. There's the tension in the horizontal rope. We know its weight, and we know its static friction. That's what this is. Okay. When asked to find the tension in the horizontal rope, it is very easy because these two have to be equal but opposite. So the tension in the horizontal rope is 1.4 newtons. Okay, and in this case it's pulling to the right, but on point P it's pulling to the left. So I'm just talking magnitudes here. Okay, later on it asks us to find normal force on A, and you should see that, like everything else in this question, because everything's equal, the normal force on A must be 6.5 newtons. Okay? In part F, it asks us to draw a free body diagram on the point itself, P, and we can do that. Remember that there is this diagonal rope, right? But we don't, like when we do free body diagrams, we normally don't deal with diagonals. We draw the horizontal and the vertical components of that rope. So this is the vertical component of tension on the diagonal rope, and this is the horizontal. Okay, so when asked to find Ft, you can determine Ftx and Fty because the whole system is in static equilibrium. And just as we always do, or have done so many times, we can find the overall tension in that rope by doing a right angle triangle, okay, and finding the angle as well. So first you do Pythagorean theorem, find out that it's 3.1 newtons, and then to find theta, it's inverse tan, opposite over adjacent, and so we have our answer, okay? And I don't know what a reasonable answer for tension is, except for that in the scope of the numbers were given in the question, 3.1 looks like a pretty good one. And as far as 63 degrees for an angle, it actually looks about right, even if you look at the original, right? Something. It's probably, if I'd gotten anywhere an answer from 40 to 70 or so, I'd say probably it's okay, based just on the picture. Okay, so that is looking a little bit at tension and also solving another system of static equilibrium.